Hi and welcome to this video. My name is Jan-Hendrik.
But you can and should call me the captain.
And in this video I would like to cover the topic OLS regression. This will be quite a long video because OLS is a huge topic to cover. Nevertheless, let's take a look what I planned for today's video. After some preliminary thoughts, I will go into OLS regression in R. Of course, the first thing we have to do is to fit a model and to interpret the results. This is what most of you will be interested in. If you don't want to go further, after let's say 10 minutes, 15 minutes, you will have this knowledge. Then I would like to have the ANOVA table for this model, and I would like to access detailed information from this OLS regression. Then I would like to go into outliers, leverage, and influential observations and how to handle them. I have to do some theory. Accordingly, I cover ordinary least squares estimators, so a little of the math behind. We need that, of course, to understand the OLS assumptions and how to check them. This is more for the use in science than for the use in practice. Nevertheless, it is always good to know about that. And, of course, the very first one, multicollinearity, that's directly combined with the ordinary least squares estimator, because if we have perfect multicollinearity, we simply can't fit the model. And that's the problem here. And of course I would like to show how to cope with that and how to check for multicollinearity, and that will be the variance inflation factors. Then we do some visual inspections in the second case because I wanted to have multicollinearity first. Then we're going to talk about heteroscedasticity and how to cope with that, how to test it and how to cope with it. Accordingly, we're going to do robust standard errors. We have to check for normality of residuals. And last but not least, we talk about the autocorrelation, but let me put this first. If we don't have any time series data, autocorrelation typically does not play a role. Well, some preliminary thoughts. What is the aim? What is the objective of OLS regression? Well, OLS regression, first of all, is a set of statistical analytics tools that aim to model relationships between a dependent variable, epsilon, and one or more independent variables.
Let me illustrate. A girl is allowed to be crazy as long as she is equally hot. Thus, if she's this crazy, she has to be this hot. If she's this crazy, she has to be this hot. You want the girl to be above this line, also known as the Vicky Mendoza diagonal.
We all know that from school, because if we have an independent variable, just like here the income, and a dependent variable, just like the wealth, we might model a relationship between those variables based on a linear function that is given here. So epsilon would be the wealth here, and the wealth would be given by a constant alpha. The constant you will find here, it's simply the intercept of the epsilon axis, plus the slope of the curve times the x value or the x values, that would be income. So maybe if we assume that we have values for alpha and beta, and if we assume that we have an income of 100,000 euro, we can simply input the income here and calculate alpha, which might be some kind of 30,000 here or 20,000, plus the slope times the income of 100,000, and we will have, let's say, an educated guess for the wealth, an estimation. So this is what we're aiming for. Of course, we can also have several independent variables, not only income, but maybe age, maybe gender, or whatsoever, so we can have more than only one x-axis. These independent variables can be metric, just like here, the income in euro is a metric variable, because we can measure it just like meters, or to cover nominal data, it can be dummy variables, just like gender, male, and female. We can input a gender variable in those models too, but of course we have to dummify it. Accordingly, we have to do a 0 or 1 coding, which means maybe the male persons get a 1 and the female persons get a 0, and then we can drop it into those models. In machine learning, regression analysis is a bit different defined. In machine learning, we speak of a regression task if the response variable, or the epsilon variable, is metric. And we speak of a classification task if this response variable is nominal or ordinal. This might be a bit confusing because we have logistic regression, which is a classification model, and it's called regression. Nevertheless, we have to keep in mind, mathematically or statistically, a regression analysis is simply a statistical tool with one dependent and maybe one or more independent variables. In machine learning, we speak of a regression task if that dependent variable is metric, and if it is nominal or ordinal, we speak of classification. We are not going to go into classification in this video because we simply speak of linear regression. Accordingly, we have a metric epsilon. The dependent variable can also be called explained variable or regressant or response variable. I already mentioned that word. And the independent variables are often called explanatory variables because they explain the behavior of the epsilon, or they are called regressors. The most common form of a regression analysis is the linear regression. Accordingly, we have a straight line if we only have one x variable, or a more complex linear function, just like a surface or a hypersurface that we are modeling here. Of course, we need some kind of methodology. We need some algorithm to fit this line to the data, because as you see here, the data is not perfectly matching the line. The data is some kind of, well, fuzzied around that line, so we need an algorithm that fits this line best possible to the data. And this method, this is what we call an estimator. Why do we call this an estimator? Because this methodology, this algorithm, estimates alpha and estimates beta, because those two parameters are needed for this line. Everything else is given. Epsilon is given and x is typically given. Nevertheless, we need an alpha and beta to draw this line, and the estimator estimates those two parameters. Accordingly, those two parameters are called estimators for alpha and estimator for beta. So an estimator is a technique. In this video, we are covering OLS regression, ordinary least squares. Ordinary least squares squares the distances between the line and the points and minimizes it. So this is an estimation technique. OLS is the estimator. Regression is more a general term of explaining a variable by other variables. So what is it for? In science, we typically use regression analysis or even more advanced techniques to explain the behavior of a certain variable by others. So we are checking the influence of certain variables on other variables. For example, of income on wealth. for example. Or, like I do it in accounting research, we typically take different ratios from accounting data, financial data, and explain the value of a company or something like that. So the output given by, let's say, R or other statistic programs, other statistic software, will be turned into those beautiful tables. And there we see those asterisks that indicate if there is a statistical significant relationship or not. That could support our hypothesis, or if there is no statistical significance, it would not support our hypothesis. But, let me repeat that from another video, we can never prove a hypothesis, we can only support it. So we find strong indicators for our hypothesis. Never ever we can prove it. That's impossible doing empirical research. Okay, so from a descriptive point of view, of course, given an exogenous variable, we fit a straight line to a two-dimensional point cloud, just like here. So this is a straight line and we have two dimensions like income and wealth. If we have two exogenous variables, of course we fit a surface to a three-dimensional point cloud, or for three or more exogenous variables, we fit a meta-surface to a high-dimensional point cloud. Of course we can't display that. So we can kind of display a three-dimensional point cloud, hardly interpretable, nevertheless it is possible even in R, but for more than that we can't display it. Nevertheless, we can calculate it, we can make statistical tests on that. From an inductive point of view, which means we want to do statistical tests, we can test dependencies. So does variable X have an effect or have an impact on variable epsilon? Does it determine variable epsilon? This is what we use in science. This is what we do in our papers. But there's also a very, very practical use for regression analysis. Predictions or forecasting. Forecasting always means in the future. Predictions means now, but we don't know the response. Accordingly, we can predict a response. So, for example, how does a country's crime rate or county's crime rate change if unemployment increases by 1%? This is quite important for police work, for example. So we want to forecast what happens to our county. Do we need more policemen because the unemployment rate is rising? Is the specified shoe size in a web store plausible to the other ordered clothing size? So if I buy my clothes in a web shop and I buy my shoes, of course the system might use OLS regression to check if everything fits to my body, and they might ask, Jan, your 186, a shoe size of 37 might not fit your feet. So we might do that in web shops. We can determine housing prices. So what price is reasonable for a house with 100 square meters? Or, for example, by how much does the wine harvest increase if the number of sunny days changes and the average temperature increases at the same time? So this might be for a winery a very important forecasting techniques, but also for climate change and so on and so forth. So as you see, we can do millions and millions of possible use cases using OLS regression. Now, I switch to RStudio and we do a little example and I show you how that works out. Okay, I've just arrived in RStudio and I prepared a little to make this video shorter. I have already done the data import. What data have I imported? I just show you. It's my most favorite data set. It's housing prices data set, real estate data set. And what do we see here? We have some kind of observation number 1, 2, 3, 4, 5. It has no relevance to us, to be honest. We have the type of the real estate of the house. We have houses, we have attached houses, and we have flats or apartments. Then we have an assessment of some specialists, if this is a luxury real estate or a normal one, luxury or normal. We have the size in square meters. We have the distance to the center of the city in kilometers. So, for example, this first house might be 5.5 kilometers away from the city center. We have a logical variable if this is a university town, universe, false or true. We have the price of the house, and we have the information if this house is already sold or not sold. Nevertheless, we ignore this last one. It's for a different video. The variable names are always VEC, like vector, a point, and then we have some word that describes like observation number, type, luxury, square meters, distance to center, university, price, and sold. Well, I have imported that data set. I can see it because here in my global environment there's the data frame, df data with 1000 observation in 8 variables. And the very first fitting of an OLS model we can do this using the LM command. LM stands for linear model. And now I have to hand over the formula, the econometric model, let's put it like this, or statistical model. I want to explain df, or I don't need that. I just can write vector dot price. Vector dot price is the variable that I want to explain, and I want to explain this variable by, so I need this little tilde, this little wave. I can access this with alt graph and plus, but this might be different with different keyboard layouts. So please, this little tilde, this little wave. And I want to explain this by the vector type. So what kind of house is this? Then plus the square meters, the size, vector size, oh no, square meters, SQM, plus the assessment, if this is luxury or not, plus the distance to center, plus if it's a university town or not. And that was it. And now, of course, since we didn't attach this data set, we need to hand over data is df data so that the model shall access this data frame. And I just run this line and I already get the coefficients. So the intercept is the intercept here is our intercept of our constant, and here we have the slopes of each individual dimension. So here flat and house and square meters. Square meters is easy to interpret because with each additional square meter the house price increases by 4,014 euros. But this is not all. I can see much more from that model if I save this model into some data type like mod OLS, and I just assign this model to this data type. I always call this a model variable, but in fact it's a list. I just run this, and now we see here on the right hand side model OLS, and it's a list of 13 elements, and we can open it and there are the coefficients in, there are the residuals in. So we have 7 coefficients, we have 1000 residuals, we have 1000 effects, we have some ranks, we have some fitted values, and so on and so forth. There's quite a lot of data in. And now we use the summary command to check what are the model results, and here in our console we get the full output of that model.
Nice!
Let us take a look into the coefficient statistics. The coefficient statistics starts with the estimates for the coefficients. So these are the constant and the slopes of the linear function that we are modeling or that we are fitting to the data. The intercept here is 24,942. It's euros, so everything here is in euros, because the epsilon axis is the price of the house, and that's in euro too. It's a bit curious to interpret because it's an intercept or a constant. So let's try. A luxury attached house with no square meters at all in the middle of the town of a non-university city would be at 24,942. Of course, that house is not existing at all. Nevertheless, it's our basis where we start. Now, of course, we can add additional square meters. Since there is no house with no square meters, we have to add square meters. And with each additional square meters, the price is climbing. So how do we interpret the estimate or the coefficient for the square meter variable? With each additional square meter, the price of the house increases by 4,014 euro. And since the p-value here is very, very low, it is below all statistical levels or all thresholds, the result is highly significant. In other words, if the result is highly significant, we typically support the alternative hypothesis and we reject the null hypothesis. The null hypothesis of these tests performed here is that the coefficient is 0. If the null hypothesis says that the coefficient is 0, the alternative hypothesis says that the coefficient is significantly different from 0, which means that with a very high probability, it's not a random effect. It's not randomly induced. So, we support the hypothesis that with the size, the price will increase. And that's quite well fitting to what we see in our everyday life, because of course the larger the house, the more expensive. So we're testing something that we already know, of course, in this case. So this is a metric variable. Square meters is metric. But in this model there are also other variables included, just like logical variables or factor variables. Both have in common that they both got dummified. Let's start with the university variable vector universe. Here we see that vector universe, there is a true appended. That means that the computer has now given the vector universe a 1 if that vector was true, or the element of the vector was true, and a 0 if it was false. So all houses in a university town have a 1, and all houses in a non-university town have a 0. And with this 1 and 0 vector, the computer estimated the OLS model. Then what we see then is a group difference. A group difference between the mean of the university city housings and the mean of the non-university city housings. So this is just a group difference. We could interpret this coefficient like this. In cities with universities, housing prices are on average 26,202 euro higher than in non-university cities. The result is highly significant because, again, here we see a very low p-value, and that undergoes all significance levels. So we have 3 asterisks here. So with a metric variable, we always have an additional unit. With logical variables, we always have group differences, coded 0 and 1. That's also 1 unit, right? Type is a factor variable. Just recall that we have single houses, we have attached houses, and we have apartments. All 3 have been dummified. So if we have a single house, the house dummy would be 1. All others would be 0. If we have an attached house, the attached dummy would be 1, all others would be 0. And if we have an apartment or a flat, the flat variable would be 1, all others would be 0. Now, of course, if we know the first 2, like it is a single house, we have a 1 here, it is not an attached, we have a 0 here, it is crystal clear that the last one must be 0. So this variable is definitely redundant. And the computer can't cope with that situation. The computer notices some multicollinearity problem because all 3 always makes the computer not solving the problem, and accordingly the computer has to remove 1. Here the attached houses have been removed, so we see the vector type flat, so the computer added some flat to that, and we see the vector type house, but there's no vector type attached. Although dummifying all 3 possibilities would lead to a third variable. Nevertheless, the computer skipped this variable since these 2 already give the full information. And this is what we call the dummy variable trap. So if you add in redundant dummy variables, the computer will remove one of them. Now, of course, the attached house that is left out here is the basis for comparison. So the flats or apartments will be compared to the attached house, and the single houses will be compared to the attached house. Now, of course, our interpretation is single houses are on average 19,257 euro more expensive than attached houses. Apartments or flats are on average 10,496 euro less expensive. It's a minus in front. These results are both highly significant. Again, we have a comparison between groups. We compare the flats to the attached houses. We compare the single houses to the attached houses. The same, of course, is true for the luxury. Here the computer chose to put the normal instead of the luxury, so we see that the normal houses are a little less expensive than the luxury houses, but this is not significant. So this 206 euro could already or also be randomly induced. It is not significantly different to 0 in this case. Although it is not included in my example, I would like to point out one important topic, and that is log transformation. Log transformation is often, really often done in empirical research, mainly because the variables are not well normally distributed, but often they are extremely skewed or they follow a completely different distribution. So like count variables, age of a person, the age of a person can't be below 0. The total assets of a company, the total assets are extremely skewed. It can't be below zero. There are many, many very small firms, and there are very, very few very, very large firms. A log transformation is absolutely necessary if you have euros or count data of any way, or even other untypical distributions. The beautiful side of the log transformation is that the interpretation still stays very easy. Well, I have the typical regression model here, where the epsilon is defined by beta 0, that's the constant, or alpha, however you like to call it, then beta 1 times x1, so here we have the coefficient for x1, the coefficient for x2, and so on and so forth. I left away all the individual indices here to make it a bit more easy to read this. And the usual interpretation, just like we have seen before, is if x1 increases by 1 unit, epsilon increases by beta 1 unit. So beta 1 is the slope on the x1 axis. So if x1 increases by 1 unit, epsilon increases by beta 1 unit. I have highlighted all those points where I would like to point at. So here x1 is log transformed. So the natural logarithm has been taken, maybe because x1 is not so well distributed. Now the interpretation becomes a bit different. If x1 increases by 1%, epsilon increases by beta 1 unit. And that's nice, isn't it? So as soon as we log transform the x, it's not unit anymore, but percent. The interpretation becomes percent. The same is true if we logarithmize the epsilon. Then we could interpret if x1 increases by 1 unit, epsilon increases by beta 1%. And what is called the log-log model, because we have logs on both sides. We have the log on the epsilon side and we have the log on the x. Then if x1 increases by 1%, epsilon increases by beta 1%. By the way, this is not connected to the other variables. They can also stay as they are. It is not necessary to transform all the variables. You can choose and only transform those variables where it is necessary. And that's the beautiful interpretation of the log transformation. Now let us have a look at the model statistics. The most important number here, of course, is the multiple r squared. The r squared is well known in statistics. It says about which ratio of the variance of the housing prices can be explained by the variances of the independent variables. That will be calculated based on the ANOVA table that you have already seen. There you see the sum of squares, and the sum of squares, of course, there's a total sum of squares and the individual sum of squares, and you can sum them up and calculate them as a ratio of total sum of squares, and that will give the r squared. So here we have an explanatory power of 0.99, so 99%. Well, that's artificial data here, obviously. In outside with real life data, we wouldn't have that high value. There is one problem with the r squared. The more variable you put into your OLS regression, the better will be the r squared. Always, with each additional variable, the r squared will become better. Accordingly, you could simply add more and more variables into your model and the r squared would be better. Nevertheless, we need something to make models comparable that have different numbers of variables. And that's the adjusted R-square. So the adjusted R-square gets ceteris paribus worse if you put more variables in. So you get punished for adding more variables in. Last but not least, there's the F statistic, which says about the model quality. And the F statistic is a test that has the null hypothesis that all estimates are 0. So this estimate is 0, this is 0, this is 0, this is 0, and so on and so forth. That's the null hypothesis. Here we have a p-value too. It's also very, very low. Accordingly, we support the alternative hypothesis that at least one of these is significantly different from 0. And of course it is, because they're mainly, with one exemption, they're all significant. Accordingly, we would expect a significant result here too. The second thing I would like to show is the ANOVA table. Okay, I show what it is. ANOVA mod OLS. No. Like this. No. Oh, I chose to do it with a point. Okay, there it is. There is our analysis of variance. ANOVA, everyone knows, it's a methodology on its own where you can make multiple testing for multiple group differences. That's typically ANOVA. Nevertheless, this ANOVA technique can also be used for regressions. So you can split the variance of the dependent variable and explain it by the variance of all independent variables. And this is typically done here. So here you have, of course, the degrees of freedom, because type has 3 levels. Here we see 2 degrees of freedom, all others have 1. We see the sum of squares. Later on we will discuss what that is. We have the mean, we have the F value, which is the basis of the test, and here we have the P value. So this is our ANOVA table. Usually it is not shown, not in business management research. Then the ANOVA table is typically not disclosed to the results. Can we get further information from our OLS model? So, no, I have to put it in there. Retrieving detailed information from the OLS model. Why is that of interest for us? Because maybe we want to write our text and we want to include some variables there. Now, how do we get our results, maybe this intercept or this coefficient? How do we get those results out of the model without copying the whole table? Especially in our markdown or our notebook, we might want to write whole sentences and include those results. So it is very interesting to get them. For example, we could start with coefficients. So if we use the coefficients command, we only get the coefficients from the model. We can use the coefficients command with squared brackets, and we get the individual value of the coefficient here. We can try the same with the next one. And there it is. So we can use those coefficients. Can we also assess confidence intervals around those estimates? Let's have a look. Confint. Of course, now we have to hand over the level, and the level, let's say 0.95, the 95% confidence intervals, and here we have the confidence intervals for our estimates. That might be quite important because we have this discussion in econometrics whether the p-value is still the valid result or if we should better show effects or confidence intervals. So here are the confidence intervals. Of course, we can also assess the fitted values. So here are the fitted values for each and every observed x value. And we can also see the residuals. And here are the residuals. The next thing we can take a look at is the covariance matrix of this model with Wyckoff. And here's our covariance matrix of this model. The next thing I would like to cover is the question of outliers, leverage, and influential observation. Let's first talk about those three definitions or those three terms. What do I mean with that? An outlier is an observation whose response or epsilon value does not follow the general trend of the rest of the data. Or, in other words, we have a very high residual. So here on the right hand side we see this data point that would meant to be an outlier because the residuals, so the vertical distance between this point and the OLS regression line would be quite high. So that's called residual. So the outlier is an outlier because it's far away in terms of the epsilon axis from our OLS regression. A data point has a high leverage if it has extreme predictor values, so extreme x values. If we look on our right hand side, here we see this yellow point and it's quite far outside on the right hand side. It could also be very far on the left hand side, but that's a high leverage observation. Of course, it is quite easy if we only have one independent variable. So with a single predictor, an extreme x value is simply one that is particularly high or low. But if we have several predictor variables, several independent variables here, that becomes more complicated. So with multiple predictors, extreme x values may be particularly high or low for one or for more predictors, or maybe unusual combinations of predictor values. Why unusual combinations? Because predictors can also be correlated among each other. So if x1 is high, it is particularly probable that x2 is high too. So a very high x1 value with a very low x2 value can also be very improbable, can also be a point that has a high leverage. Of course, calculating some kind of indicator for leverage, and we will come back to that too, becomes more complicated if we have two or more predictor variables, if we have two or more x values than only one. If we have only one, we only look at the very high and very low numbers. But as soon as we have 2 or 3 or 4 independent variables, we have to find something different. I will not go too much into the math, but there is an indicator that is called leverage, of course, and that is calculated as the diagonal of the hat value matrix, but let's not go too much into that. A data point is influential if it unduly influences any part of a regression analysis, such as the predicted responses, the estimated slope coefficients, or the hypothesis test results. Outliers and high leverage data points have the potential to be influential, but we generally have to investigate further to determine whether or not they are actually influential. What do I mean with that? Let's take a look. Let us assume, additionally to the red data dots here, we have this blue outlier here. How would that affect our regression line? Let's take a look. Here with a dotted line, we see the new regression line under the assumption that this is a real data point. So the outlier, of course, would pull the whole line a little up. What is affected? The regression constant, of course. That can already be influential, of course, but maybe not. So, maybe we have a problem, but maybe we don't have a problem. What about the high leverage observation that we have here? Seemingly, this high leverage observation, this yellow point, is very much in line with the OLS regression. So, if you now watch closely, you see the yellow dotted line. So the OLS line is not affected at all. Of course, this high leverage observation might also unduly affect the regression. In this case, it doesn't do, because it is in line with the regression line. But now let's take a look at this influential observation. Seemingly, this influential observation combines both. It is an outlier as well as a high leverage observation. And what happens to the regression line here? Wow, that really deteriorates our whole OLS regression. We see a different constant and we see a different slope. Definitely, this line has nothing to do with the data trend here. So it's just like a compass needle with a magnet here, and that doesn't work together. So we have to find ways to find outliers, to find those with high leverage observations, and to find influential observations. Typically in accounting research, but I think in many, many other research streams, Vinsorization is the usual thing that is done here. Vinsorization means setting very far outliers on one axis closer to the middle. So let's take the 1% there and the 1% there and put them on the 1% percentile. So that takes away their power or their influence. Nevertheless, if we take a look at this yellow point and we would Vinsorize this one, so put it on the 1% percentile, that might be somewhere here, that our high leverage observation would get, I think, even more destroying power than it has now. So even for Vinsorization might deteriorate your OLS regression too. Now let's take a look how we can do that in RStudio. I just switched to RStudio and let's see how that works out. Okay, I've just arrived again in RStudio, and now I would like to do some outlier, leverage, and influential observation analysis. Okay, and now of course the first thing that we should analyze is the leverage. Now the first thing we should analyze, of course, are the residuals to find outliers. And of course we can use the residuals command and hand over our OLS model. Let's run this, and there are the residuals. And now we can make a little trick. We can define a vector of residuals and just store those residuals in there. And now we can use the view command that we typically use for data frames to take a look at those residuals. And here's our vector of residuals. And now, of course, I can sort them like this, and I find those observations 854, 270, 217, 908, so those with very, very high residuals. These are the outliers. The same, of course, is true on the other side of the axis. Here we have those with very high positive residuals, while on the other side they were negative. So this is a very nice method how to find outliers, so those with very extreme epsilon values. The second thing, of course, is leverage. And as I said, it is quite complicated to find an indicator for leverage. We have to go deeply into matrix algebra, what I don't want to cover here. Nevertheless, we can find an indicator for the leverage with the het values command. The het values command is the diagonal of the het values matrix here. And of course, we have to hand over again the model OLS, and here are the het values. Again, I apply vector het values and hand over this command. And again, I use the view command. Didn't I run that line? There it is. And again, I sort those values. And now, of course, those with very, very high leverage, I just scroll down. I will find down here. And of course, I can check those if they really deteriorate or bias my OLS regression. Last but not least, we could combine these two ideas, residuals and leverage. And Cook already did this for us, so we can calculate Cook's distances. And Cook's distances is given with the Cook's distance command. Here are Cook's distances, and again, a vector Cook's d. I store all those in this vector, and I view the vector. And I sort the vector. And of course, now I find those with very high Cook's distances here. And I can check if they are influencing my OLS regression. How do I do that? Of course, I could now, let's say, remove the first 5 or 10 observations or highest observations here with the highest Cook's distance, run the OLS regression and check if the results are very much different, especially if we lose statistical power in terms of significances. Of course, it is a bad situation if that way my hypothesis variable is not significant anymore, but that's the way life is, right? Sometimes our results are simply induced by outliers, and that's the way we could also cope with it. So version number 1 is Winsorization. I have already mentioned what that is. Version number 2 is checking Cook's distances, leverage, and residuals, removing, let's say, those that are very extreme. By the way, can I see what is extreme? Of course I can. I use the plot command. I just go back into the code. And I have to hand over the 4 and run this. And here I get Cook's distances and the very extreme values with Cook's distances. And we see 854 is very, very extreme. I think 94 and 11 are also extreme. So why not remove those 3 observations? The rest is seemingly very much in line here. Remove those 3 observations and check whether they have influential power on our OLS regression results. That's a good way to handle the problem of outliers, leverage, and influential observations. For a better understanding of the OLS method, it is quite good to understand the OLS estimation, especially since we want to understand the OLS assumptions later on. Let's make that very easy. As you see, I changed a little the writing of my linear function because I now want to explain each and every data point. Not the points on the line anymore, but I want to explain each and every data point now. To do so, of course, I need indices for those points. We have 9 points here, and I would like to have 9 indices, each for every point. And I take the example of this point. It's the 7th point. That's why I use the index 7 here. Now let us see how I can explain the epsilon value of point 7 with the data that I have. So the epsilon value of the 7th point is composed of alpha, our regression constant, so we start here. We go from 0 to alpha. Then we go x7, so the x value of 7 to the right. And we go beta times x steps upwards. So beta is the slope of that line, and accordingly we go up x7 times beta. Then we end up in that point on the line, the estimate for this x value. And then of course we add the residual or the error of this point. Accordingly we need this little epsilon here. It's the error of 0.7. So like this, I can write down a formula that gives us the epsilon value for all data points using those indices. Of course, alpha and beta are valid for all points, so there is no need to give them any index, only the epsilon value, the x value, and the error or residual need to have this index here. Well, if we now write this in a very general form, we can write down that the epsilon value for any of those points, for all of those points with an index I, so this index I counts from 1 to n, so I can simply insert 1, 2, 3, 4, 5 up to n into this index. By the way, this operator means for all. So this formula is valid for all I from 1 to n. So for each and every of those points, the epsilon value, epsilon I, can be explained by alpha plus beta times xi plus the error term. So this is mainly the idea. And this, by the way, is what we call an econometric model. These econometric models are always displayed, and in every paper that you read, in every empirical paper, they are typically given. Often different forms of these or different variations of those models are shown later on. Nevertheless, the base model is always shown with a formula like this. Although often the variables have names like wealth or income, they are often not called epsilon or x, but epsilon and x is more for a beginner to understand. This is the x-axis and this is the epsilon axis. Later on, we replace them by variable names that we can understand, of course. Nevertheless, we stick with the indices, we stick with the alpha and betas. Sometimes alpha is replaced by const or something like that, or beta 0. That's also very nice. And often the betas are numbered, so this would be beta 1, and if we have several x, there's beta 1, beta 2, beta 3, and so on. Well, now of course, to estimate such a line, to make such a function, we need to find a value for alpha, and we need to find a value for beta. Well, let's see how we can do that. The idea, the basic idea here is now to find the line that has, let's say, the least distances, the least residuals here, but some of these residuals are positive. All those where the points are above the line, we have positive residuals. And all those points that are below the line, the residuals are negative. Well, since the error term can be positive and negative, we have to find something like an overall error, and that we can achieve that by simply squaring those errors, squaring those residuals. And that's where the word comes from, ordinary least squares estimators, because we square those residuals and we minimize them. That's why we speak of least squares. Now let's see how we can achieve this. Now we start, I just left away the I and C that I annotated here, and I gave it a more general approach nevertheless. So the epsilon, again, is explained by alpha and beta, the x value and the residual. Now, of course, we arrange the equation and isolate the error term so that we have the error term given by epsilon minus alpha minus beta times epsilon. So just bringing alpha and beta x on the other side. That's it. Of course, we have to do this for all data points that we have. Since this is only for one data point, for the ith data point, can be the first, can be the second, but it's not for all of them, we have to do that for all data points. Accordingly, I use the sum sign, and I sum the errors for all data points, and I don't only sum the errors, I sum the squared errors. Ordinary least squares. I sum the squared errors. The same happens on the right-hand side. I have to use the sum sign and I have to square the whole term that we have here. I gave all that a little abbreviation, RSS, and RSS stands for residual sum of squares. So the residual sum of squares quite plays a crucial role in many calculations, on OLS calculations. That's why I show it like this. Now, of course, we want to minimize RSS. We want to minimize the squared errors. Well, it's a lot easier if we do not start multiplying out the brackets here. Don't do that. We have a more feasible way to do so. So now we want to minimize RSS by choosing the right alpha and choosing the right beta. We have a minimization across two variables. Most of us have already learned at school how that works out, so we have to derive that formula with respect to alpha and with respect to beta. Both derivations have to be set 0. That's why I have this exclamation mark here above the equivalent sign. We have to set them 0. Both of them. By setting them 0, the derivations become first order conditions. So this is our first order condition, and this is our second first order condition. Of course, depending on how many explanatory variables you have, how many x variables you have, you will have more and more first order conditions. If we now look at this, of course the -2 is redundant in both equations because you can simply divide by -2. 0 divided by -2 is still 0, and the left hand side you can just remove the -2 here. So the first order condition can be simplified like that. If we now rearrange our two first order conditions the way I did it here, you can see something. And I highlighted all that with the yellow ink here. Well, if you rearrange your formula just like this, you will notice that the yellow highlighted parts of the formula are well known because they are simply based on the data that you have. Here you have, for example, the sum across all epsilon I. Here you have the number n, number of observations, and here you have the sum across all xi's. We know all that. We can simply calculate that because we have an Excel table about all xi's and all epsilon i's. The same is true here. X times epsilon. The same is true here. The same is true here. So what do we have here? Here we have a linear system of equations, or a system of linear equations. We have one linear equation and we have a second linear equations. And of course we can solve this system of linear equation, given the case that it is solvable. Given the case that it is solvable, is that self-explaining? No, it is not. There are cases, of course, where this system cannot be solved. We all know systems of linear equations from school. Typically we have two crossed lines, and the solution to that is the intercept, or the crossing of those two lines, the point where the two lines get in touch. But of course, if those lines are perfectly parallel, it is not solvable. You won't find any solution for that. Well, and that is possible here too. This is the case when we have multicollinearity. And that's very much the reason why we have to understand the OLS estimator to understand what multicollinearity means to our OLS estimation. Well, we don't have to go into how to solve those systems of linear equations, because Excel can do that. Each and every program can do that. You simply use Gauss algorithm or something like that, and you can solve that if there is a solution, of course. We call those equations normal equations. So this is our first normal equation, this is our second normal equations, and we have many, many more normal equations the more explanatory variables we have. Well, that's it for the ordinary least squares estimation. But there is one additional information that I want to give you, and that is only for the univariate case where you only have one explanatory variable, because you can rearrange those formulas very, very beautifully. And let me show you how that works out. Of course, now I would like to have alpha first, and now I rearrange the first order condition number 1 so that I isolate alpha. Isolating alpha from the first order condition number 1. And that's quite easy, because I can just write alpha is, now of course I have the sum, I make my life easy, across all i's, epsilon I, and of course I have to bring this to the other side. Accordingly, I have a minus beta times the sum across all I xi, and we have to divide by n, so I use brackets and divide by n. So this is the first step, and the second step is self-explaining. I have to get rid of the brackets, so alpha is given by 1 divided by n, the sum across all I, epsilon I, minus beta, the sum across all I, xi. And that makes our life extremely easy, because now alpha is, let's see what this is. We have to divide by n, by the number of observation, and we sum across all epsilon. This is the arithmetic mean of epsilon. So this is epsilon bar. Then we have minus beta. And I've just forgot the 1 divided by n. Sorry for that, of course. That's important. Since this is 1 divided by n and the sum across all xi, this is the arithmetic mean of x, so it is x bar. So we have a very simple solution for alpha, very, very simple. And we can learn something from alpha, because we can learn that alpha goes through the point x bar epsilon bar. So the point x bar epsilon bar, this is what I typically call the center of gravity. And of course the regression line now passes the center of gravity of our cloud of points. What's the center of gravity? It's exactly that point where we can balance an object or the cloud of points on our finger. And it's exactly where all the arithmetic means can be found, like x bar and epsilon bar. The second step now, of course, I need a bit more space for this, is inserting this result into the first order condition number 2. Now, how can we do that? Of course, we take the same formula that is already given, the sum across all xi epsilon I is given by, and now we replace the alpha by our result that we already achieved. So epsilon bar minus beta x bar. So this alpha is replaced by this result here. Of course, we have to multiply this by the rest of the formula here, or add the rest of the formula here. So times the sum across all I xi plus beta times the sum across all I xi squared. Well, of course that is quite easy. Now we want to get rid of the brackets, of course. We sum across all I xi epsilon I, and now we have epsilon bar, this one, times this sum across all I xi. We have minus beta x bar times this, beta x bar times the sum across all I xi, plus beta sum across all I xi squared. Now the idea is to implement this 1 divided by n simply by multiplying all the terms, both sides, by 1 divided by n. So we have 1 divided by n, the sum across all I xi epsilon I. So this is the left-hand side of the equation. Now I use the right-hand side of the equation. I take the epsilon, then I divide by n, sum across all I xi, minus beta x bar, 1 divided by n, sum across all I xi, plus beta 1 divided by n, sum across all I xi squared. And now let's have a look what we have. So this, of course, is the arithmetic mean, because we divide by n and we sum up all xi epsilon I. So this is x times epsilon bar. Then we have epsilon bar, and then we have the arithmetic mean across all x, so we have x bar here. Then we have minus beta x bar, and we have again x bar, plus beta, and what do we have here? We have the arithmetic mean of x squared. So we have x squared bar. Of course, here this is x bar squared. Don't mix this up. So x epsilon bar is not the same as x bar epsilon bar. So these are different numbers. And x bar square is not the same as x square bar. Also, these are different numbers. Now, of course, we can now isolate beta. Beta is now given by a fraction line where we have x epsilon bar minus x bar epsilon bar divided by x square bar minus x bar squared. And we already know these formulas from 2 other videos. We now have the covariance between x and epsilon, so as x epsilon, and we have the variance s squared of x. So this is the covariance of x and epsilon, and it is divided by the variance of x. So this is the slope of our regression line in a simple regression with just one explanatory variable, that would be x. And that's a very, very nice simplification because we can simply calculate those numbers. We don't have to solve a system of linear equations, and that makes our life a lot easier. As already indicated, one problem with OLS estimation directly comes from the minimization or optimization problem that we've just seen when calculated OLS estimates. And that's the problem of multicollinearity. We speak of perfect multicollinearity if two or more variables are perfectly correlated. They are perfectly redundant, or they're perfectly negative correlated. And this is exactly what we see when we speak of the dummy variable trap. If we have, for example, a dummy variable with, for males and females, the male variable is 1 if the subject is male, the female is if the subject is female, they are always redundant. If we know that this one is male, this one can't be the same, cannot be female, and vice versa. Accordingly, these two dummy variables are perfectly negatively correlated. And due to that, we have the problem of multicollinearity. This leads to the problem that the system of normal equations has no solution. This is exactly what we had at school when we tried to solve a system of linear equations, and those linear equations, the graph of those linear equations was parallel. Well, what happens then if we have perfect multicollinearity in our data? The computer will notice, and in some software packages we will get an error, but in most software packages one of the variables will be removed. Please pay attention to that. So if you show in your paper a certain econometric model and some of those variables will be removed, that econometric model and the result tables do not fit together anymore. So please check that. That's very important here, right? But the computer will let you know if the computer removes certain variables. So this is not really a problem. The computer does its job and removes the variable. A bigger problem, a much bigger problem, is imperfect multicollinearity. That means these variables are highly correlated but not perfect. And accordingly, let's say in this graph here, these lines are not perfectly parallel but close to parallel. What happens if those normal equations are nearly parallel? A very slight, let's say, shift or tilt of one of those equations, of one of those lines here, will lead to the solution jumping up or down. So easily, with a little tilt, this intercept will go quite a long distance in this graph. So our results will become unstable. Very, very unstable. And so they can change substantially when variables are added or dropped. And of course, the variances and the standard errors of our regression coefficients will increase. So this means lower t-statistics. We lose statistical power here. Now, how can we recognize imperfect multicollinearity? There are 3 methods how to do that. Of course, the second thing that we are calculating in our descriptives is a correlation matrix or a correlation table. And high correlation coefficients, as a rule of thumb, higher than 0.8, might indicate severe multicollinearity problems. Another strong indicator is high R square with low t-statistic values. this is exactly what I just told you. We have a high volatility in our system, reducing the t-statistics, but still the R-square is high. That's a curious situation. Keep that in mind if you see that and you can't explain. This might be the reason. But the best solution to this problem is to calculate variance inflation factors. Let me show you what variance inflation factors are. The idea of variance inflation factors is extremely simple. Let us assume this econometric model. In this econometric model, I left away all the indices indicating individual data points. So there's no epsilon I just wrote epsilon here. Those indices that you see number the number of variables. So we have an x1, we have an x2, we have an up to xk, and for each x we have a beta factor to estimate. And of course we have a beta 0, that's our constant, that's our intercept here. If now x1 and x2 are highly correlated, they have something in common, right? They have something in common, even controlled for all other variables in the system. Now the idea is, if that is the case, let us set up a different OLS model. Let's remove the epsilon and let's put the x1 in here. What happens then? If x1 and x2 are highly correlated, x2 will be able to explain x1 quite well. Accordingly, an OLS regression with x1 as explained variable will lead to a very, very high R-square. We have removed the response epsilon and we have shifted the x1 to be the new explained variable. And now x2 will explain x1 extremely well if both are highly correlated. Accordingly, in this econometric model, the R-square will be high, and the variance inflation factor for beta I, or in this case, of course, beta 1, can be calculated by 1 divided by 1 minus R square I. R square I is the R square of this regression model. Now, if this R square is very high, it is close to 1. 1 minus something close to 1 will give a very small number. 1 divided by a very small number will be a very high number, of course. And now here we have this beautiful traffic light, and that says exactly how to interpret those variance inflation factors. As long as the variance inflation factors is below 4, we have a green light. Everything is fine. If we have a variance inflation factor of larger than 4 but smaller than 10, well, we have to keep that in mind. It can already induce some instabilities, and definitely with a variance inflation factor of larger than 10%, of 10, we should not work. We should remove the variable. And of course, for each and every econometric model with, let's say, k explanatory variables, we will have k variance inflation factors, so we have to check them all. Let's see how that is done in R. I have arrived in RStudio again, and of course I just write variance inflation factors 1, 2, 3, 4, 5. And the first thing is we need the library car. Alright, that was loaded. If that is not yet installed on your computer, of course you will need to install it. Install.packages, in brackets, in quotation marks, car. But since this package is already installed on my computer, I don't need to run this installation routine. I just comment it, and if not yet done, install packages. I always put it there because I often share my code with students or with colleagues, and they just have to use the enter, and then they have the install package command there. They will be reminded to install it, otherwise they will run into an error message, and this one is really of help. Now, since we now have installed the library, we can use the VIF, Variance Inflation Factors command, and we have to hand over the model OLS. I run this, and here are our variance inflation factors. They are all below 4, so I don't have any problem with my multicollinearity in my OLS model. The next topic on my list is to make a visual inspection of our regression model. And it is extremely easy, so there's a simple command, and that's the plot command. And we hand over to the plot command simply our OLS model. So the mod OLS list or command. Well, and now we see it's in German. We should press enter. Now I press enter and I get this beautiful graph here. So what do we see on this graph? We see the fitted values on the x-axis, and we see the residuals on the epsilon axis. And of course, this is very much a plot where we can detect heteroscedasticity. Here, seemingly, we don't have a big problem. We would have a problem if we would have some kind of triangle pointing to the left or triangle pointing to the right. But we don't have it here, so they are beautifully distributed with quite a very constant variance. So we don't have a heteroscedasticity problem here. Beautiful graph. Nevertheless, we are again asked to press enter. I press enter, and here we see a QQ plot, or in the headline or in the caption we see normal QQ, which means that this is a QQ plot testing for normality or visualizing normality. How does a QQ plot work? We see the theoretical quantiles on the x-axis, and we see the standardized residuals on the epsilon axis. So if the theoretical quantiles, like in the normal distribution, and the standardized residuals match, you will find all points on the diagonal line here. And this is very, very much the case. So here maybe this one a little deviates, but that's pretty usual that here in the tails you see little deviations. Nevertheless, this is nearly perfectly normal. If the line of dots and the diagonal, the dotted line that you see here and here, if they deviate strongly, if they deviate significantly, you have a problem with the normality of your residuals. I will get the next plot just by pressing enter, and this is very, very much like the first one. Here we see the fitted values again, but now we see the square root of standardized residuals. Nevertheless, trumpet alike or a left or a right tipped triangle would not be that good. Nevertheless, this looks beautiful. But let's see the fourth one. The fourth one is very closely related to influential observations, because we have the leverage. And we know that leverage can lead to an influential observation. We have the standardized residuals, and we know that large residuals can lead to influential observations. And in red line here we see Cook's distance. Honestly speaking, we can't really see it like this. It looks a bit like a fingernail typically. So we see Cook's distance as a kind of frontier, and every data point outside this frontier has a large Cook's distance, and should be checked for its influence. In all those graphs, you will see points with numbers indicated. So that's the observation number here. And so in this graph, you will be led to check number 95, 11, and 854. Seemingly, they might have an influence on your OLS regression.
That is so awesome! A high five doesn't even cut it. High six! Assistant.
She didn't see us high six, did she?
No. Good, that was pretty lame.
Okay, the next topic on our list is homoscedasticity and heteroscedasticity. Obviously, homoscedasticity is the opposite of heteroscedasticity. Let me just briefly illustrate what that means. So, we start with homoscedasticity. And we need a little graph here, and of course we have variable x, that's our exogenous variable, and we have epsilon, that's our endogenous or response, we have our regression line, and we have our data points somewhere around those OLS regression line. Well, as we see here, if I just add some, let's say, error bands to this, these error bands are parallel. These error bands are parallel to our regression line. So that means that the residuals are roughly the same if we look here, the same as if we look here. Accordingly, the variance of, let's say, our error term, we can call it UI, or we can also use a Greek if we want to, given xi is a constant. It is the variance. If we now look at heteroscedasticity, let's show it here. Again, we need the same graph. Of course, we have the x, we have the epsilon, we have our regression line, but now we have observations that looks like this trumpet-alike form. Just like this. And if I now add some arrow bands, it's more than obvious that the residuals here get wider with x. So heteroscedasticity means that the variance of the error terms given x is not constant, but is some kind of function of x and other parameters. It can be a trumpet looking to the right, it can be a trumpet pointing to the left. However, nevertheless, they are not constant. So that is heteroscedasticity. Well, what's the problem with heteroscedasticity? It's obviously a problem of testing. Since our t-tests, our coefficient tests, are all tests based on the variance of our residuals, it is a problem if our residuals are a function of the x value here. Why that? Because our test is based on some kind of middle constant variance, so our test assumes that the variance is constant. So in certain regions, like here, obviously our test result underestimates the variance, and here it overestimates the variance. And that's, of course, that's a big problem here. Let's go to our studio and let's test, or let's make a test for heteroscedasticity. Okay, I've just arrived in our studio and I've given you a headline. And the test that we want to perform now is the Breusch-Pagan test. And of course, it is always crucial to know which is the null hypothesis in those tests. So the null hypothesis here is that the variances of the error are constant. And of course, the alternative hypothesis here is that the variances of the error are non-constant, or in other words, we have heteroscedasticity. Well, of course, we need a certain package for that, and that's the LM package. So I can start it with library LM test, and I can run this line, and I just started LM package, or the LM test package. If this package is not yet installed on your computer, of course you have to do that by install packages and in brackets and quotation marks LM test. But since this is already done on my computer, I don't need to reinstall that. I just comment it, and if not yet done, so if I share this code with my students and they haven't installed it, they get reminded and they just can enter it, have the command, and put it back into the command. Well, and now we can start our test. It is BP test. And I hand over the model, our OLS model variable, and I start this. So, here's the results. Studentized Breusch-Pagan test, and we have a p-value of 0.34. So this does not support the alternative hypothesis. We stick with our null hypothesis, and our null hypothesis was that the variances of the error are constant, and that is homoscedasticity here. So no problem with heteroscedasticity. But, honestly speaking, this is not a real-world case. So in the real world, we nearly always have a heteroscedasticity problem. How can we cope now with heteroscedasticity? We can use heteroscedasticity robust standard errors. So we can correct that. We can correct the standard errors and make a robust test. Often they are only called robust standard errors, but the full writing, of course, is heteroscedasticity robust standard errors. Long word. Alright, so what do we need? We need another package. We need the package sandwich. And I just run this, and it was loaded. Again, we need the same like here. So if it is not installed on your machine, you will need to install it, and of course that would be sandwich then. But I don't run this line because it is already installed here. And again, we need the LM test package, so I copy all this too. So we need these two packages, the sandwich package and the LM test package. The first thing that we are going to do now is to calculate a new robust covariance matrix. So a covariance matrix, let's put it like this, covariance of our OLS model. So this is just a data structure. I'm going to save it in. It's a matrix. And the command here is vcov, just like the vcov command for getting the covariance matrix from the OLS matrix, vcov, And additionally, we add HC. And then we hand over the model OLS, and we have to hand over the type of correction here. The type of correction typically goes back to white HC0. Let's use this one, HC0. It's a bit old-fashioned, HC0. The standard here is HC3. Nevertheless, what's the difference between those types? They have different corrections for small samples. Nevertheless, we have a large sample here, and if the sample is large enough, those types, those HC corrections, they converge to each other, so they deliver mainly the same results. Only if you have small samples, please check which of these correction types is the right for you to use. Alright, I run this line, and now I have here the covariance matrix, the robust covariance matrix, and seemingly it's a 7x7 matrix, numerical matrix here. Well, now we can calculate the robust standard errors, and I'm going to save them in one of those data types too, for our OLS model, and that is always the square root of the diagonal of this new covariance matrix. And let's see how they look like. Oh, I'm sorry. SQRT. There's a T missing. Now I run this and print, and here are our robust standard errors. And now, of course, we want to make a test based on those robust standard errors, and that's what we need the LM test for. There we have the coef test command. For the coef test command, we need the model, and we need the covariance matrix. And we run this, and now we have a coefficient test, especially here on the right-hand side. We have those coefficient tests based on robust standard errors. The next topic now is the test for normality of the residuals. Okay, so let's give it a headline. Well, why do we have to test for normality? We make a t-test. And accordingly, if we make a t-test, we assume that the variable we are testing on, and that's the residuals here, is kind of normally distributed. Otherwise, we cannot use a parametric test. We would need to have some robust test, some non-parametric test. But the t-test is parametric. It's based on the t-distribution, very closely related to the normal distribution. And, well, we have to test for normality here. Well, all tests that I would like to show have the null hypothesis of normally distributed, a normally distributed variable. The alternative for hypothesis here is non-normal distribution. So they have all that in common. The very first test, maybe every one of us already had that at introductory courses, is the chi-square test. That's Pearson's chi-square test. Well, to do that, we need a package again, and that's the NOR-test package. I can start that package. Oh, no, it's not installed. Okay, let's install it. Alright, there it is. Now I can start it. And I comment this if not yet done. So everyone knows we need to install this package. Well, that's the package we need. A little more distance would be very nice here. And of course, we can now start the test. But first of all, I would like to have a vector of residuals. Oh, I already have that. I have that vector. Nevertheless, residuals, I rewrite that, residuals of our model OLS. I save those residuals, and now I have the vector of residuals here, 1000 residuals. And now I test those residuals using Pearson.test, and I hand over the vector of residuals and run that test. Pearson chi-square normality test, and the p-value here is 0.49, which means that we still stick with our null hypothesis. It is normally distributed. If we would now go under one of our thresholds, like 0.05, like 5% significance level, then of course we would support our alternative hypothesis and reject null. That would mean that we don't have a normal distribution then. Well, that's a pretty simple test. It is not very specialized on residuals, so it is not perfectly fitting to OLS analysis. The next one won't be either. That is the Kolmogorov-Smirnov test. And the Kolmogorov-Smirnov test is also in the NOR test package. So I just copy this part here. And I can test now using ks.test for Kolmogorov-Smirnov test. And of course I hand over the vector residuals here and run this. Of course, I forgot. I have to hand over the function rnorm. That means we have a normal distribution. We can also test for other distribution. And I have to hand over the alternative. And that is that we want to have a two-sided test here. And now I can run it. And there it is. We have a very, very low p-value here. That's very typical for Kolmogorov-Smirnov. So the alternative hypothesis is supported here. And nevertheless, don't worry about that. First of all, Kolmogorov-Smirnov is very, very, well, I don't know. It's very hard not to get the alternative hypothesis here. And it's not very well suited to test residuals. But there's a better alternative for that, and that is, I simply copy all that. The better alternative, and now it becomes more important for you, is the Kolmogorov-Smirnov-Lilliefors test. Of course, that is also in the NOR test package. I have to run that package, and then the command is Lilly. But I only have to hand over the residuals, that's all. And run that test. And here the p-value indicates a normal distribution again. So don't worry about that. So if you use this for OLS diagnostics, please always use the Lilliefors test and not the classical Kolmogorov-Smirnov. The Lilliefors test is for OLS diagnostic especially. Well, there's another one. That's the Jark-Bera test. This one is also well suited for OLS diagnostic. It's especially invented for that. Explicitly for OLS diagnostics. And I copy this to the Liliford because that's true for that one too. We need a different package here, unfortunately, and that's norm test. Norm test. And of course, if that is not installed on your machine, if not yet done, install packages norm test. Just like that. And now we can perform the jog-bearer jb.norm.test, and again we hand over the vector of residuals, run the test, and there we get the p-value for the jog-bearer normality test. Beautiful! So, the next test I would like to show is the Shapiro-Wilk test. The Shapiro-Wilk test is a test in the stats package, and the stats package is always installed. It comes with the RBase, so we don't have to install any package here. And that is Shapiro test, of course. And again, the vector of residuals. I run this and I get the p-value. We stick with our null, normally distributed. But again, the Shapiro-Wilk test is not well suited for OLS diagnostics. There is a better alternative. Again, we need the NOR test. That's why I copy this. And of course, what's that? It's the Shapiro-Francia. Or Francia? I don't know. And again, we need the NOR test package that I've already run. And that's then the SF test. So here's the Shapiro-Francia or Francia normality test, and the p-value is 0.79. Still stick with normality. Last but not least, I would like to introduce the Anderson-Darling test. The Anderson-Darling test is again in the NOR test package, so I copy that here. And we need ad.test and the vector of residuals and run that. And again, there's the p-value 0.811. We stick with our null normality. Well, that was quite a lot. Nevertheless, you will need one or at max 2 tests. Simply do what the authors of your key paper have done, but in most cases you won't find any information about that, because with especially with accounting and financial data, with stock-based data, you will never have a normally distributed residual here. But as long as you are close, so simply check that visually, plot a histogram just like this. Hist just plot a histogram just like this, and if this looks more or less normal, you will be fine. If you have a very skewed distribution here or extreme outliers, then please check your data. But as long as you're close to normal, don't worry about that. So I have nearly never read any paper that checked for normality, so typically it's because they don't have normally distributed residuals. Well, the last topic I would like to cover is autocorrelation. But is autocorrelation really a problem here? Let's see. So what we are currently doing is OLS regression. And OLS regression is typically used for a cross-sectional analysis. What does that mean? Cross-sectional analysis means that we check many individuals or many observations, but all at the same time. So if we look at this graph here, we see different individuals. So this is our first individual, this is our second, our third, and so on and so forth. And with cross-sectional analysis, we maybe ask those people, we make a survey, but all of them at the same time. That is cross-sectional analysis. Autocorrelation means a correlation inside one individual. So if the year before influences this year, that's autocorrelation. And the problem of autocorrelation we're covering now means that we have some correlation within the residuals, typically induced by a time series effect, typically induced by seeing an individual several times in our sample. But in cross-sectional analysis, we don't have that. So, no problem. If we have a typical structure like we often have it in accounting or financial research, just like this, we see several firms, but we don't see them at the same time. Nevertheless, they're in only once. If they're in only once, so individual number one is in, let's say, in the year 2020, individual number two in 2019, this one in 2021, and so on and so forth, but they're in our sample only once. Of course, we have an effect of time, definitely. So in 2019, maybe we had a bad year, in 2020 we had a good year, and in 2021 we had a bad year again. So time induces effects in our data. Nevertheless, that has nothing to do with autocorrelation. We are still cross-sectional. We can cope with this problem by setting time dummies. One time dummy for 2019, one time dummy for 2020, and of course, due to the dummy variable trap, we have to leave out one, so the newest or the oldest would be the best choice here. Nevertheless, no autocorrelation problem. As soon as we do some time series analysis, just like here, we see one individual each and every year. Of course, we might have autocorrelation problems, but that's a question of time series analysis, and that's not a question of OLS regression here. So time series analysis can cope with the problem, OLS can't. So, but we don't have an OLS problem here. Where we do have our autocorrelation problems is in panel data analysis. Panel data analysis is very closely related, in my field, it is very closely related to OLS regression, but we have each and every individual quite often in there. So we might induce autocorrelation problems. Well, there is a check for autocorrelation problems, so let's take a look at that in our studio. I'm back in our studio, and I just add that. And the test for autocorrelation is a standard test here, that is the Durbin-Watson test. And the Durbin-Watson test is DW test mod OLS. So I hand over my model variable and I run this and I get this result here. Alternative hypothesis is true, autocorrelation is greater than 0, but nevertheless the p-value here is 0.45, so we stick with the null hypothesis, and we can look at this DW Durbin-Watson statistic. If this is close to 2, and this one is really close to 2, we don't have any autocorrelation problem. We stick with null, no autocorrelation problem here, and the DW statistic is very close to 2. Thank you for watching this video, and see you in the next video.
Tiny 5.